Good morning, friends. Today we are discuss about advanced foundry technology. This course is material is designed for MSc Mechanical Engineering for manufacturing students in Bhagirath University. So my name is N. Sri Rangarajulu. I am assistant professor in this department of production technology, MIT campus, Anna University, Chennai. So today we are discuss about the special casting techniques for advanced foundry and welding technology. So we are discussing about the objective of this study, give good perspective with adequate depth to understand casting metallurgy and design, special casting processes, and including recent advances in casting. So today's course outline, already we are discussed about the patents and the patent making in previous video. Molding also we are discussed in the previous video. So today we are discuss about casting processes and special casting processes. Okay. So today we are discuss about special casting processes. What are all their applications, advantages, limitations, and so on. So casting processes and special casting processes. The casting processes, physics and constraints, phase changes, density, solubility, diffusion rate, high melting temperature, chemical activity, high latent heat, handling. These are all the things are important. So analysis of casting processes, fluid mechanics for mold filling, heat transfer for solidification, thermodynamics, mass transfer and heat transfer for nucleation and growth, material behavior for structure property relationship. These are all the things we can able to applicable in the fluid mechanics, heat transfer, thermodynamic, material behavior. All those things are incorporated. Then only the casting process will be obtained. So categories of casting processes: expandable mold casting, mold made up of sand, plaster, or similar materials whose form is maintained by using binders, in which the molten metal solidifies, must be destroyed in order to remove the casting. For example, sand casting method. So permanent mold casting, mold made up of metal or a ceramic refractory materials, is one that can be used over and over to produce many castings. The mold can withstand high temperatures of the casting operation. The mold consists of 2 or more sections that can be opened to permit removal of the finished parts. Example for die casting method. There are categories of casting processes. There are expandable mold, material mold, centrifugal casting, and low blast foam casting, investment casting, replicate process, counter gravity process, hot chamber die casting, cold chamber die casting. So many varieties of casting processes are there. This is the flow diagram of different types of casting processes. So today we will discuss about some of the special casting processes. So first we will discuss about sand casting processes, sand casting method. The most widely used casting processes, nearly all the today we are discuss about sand casting process. Most widely used casting process, nearly all casting alloys can be sand cast, that is ferrous material, non-ferrous materials, as well as plastics, whatever it may be, we are able to make a casting. It can be used for material with high melting temperatures such as steel, nickel, titanium, etc. The versatility permits the casting of parts ranging in size from small to very and in production quantities from 1 to millions. It is also known as sand mold casting process. Next, we will discuss about the sand casting methods. First, we will make a core making and preparation of sand, raw material melting. After that, they will make a pattern making and mold making. Then you can pouring the molten metal, solidification of cooling, removal of sand mold, cleaning and inspection. Finally, we will get the finished casting product. This is the steps in the production sequence in sand casting process. So, sand casting method, they will have an open riser, vent, pouring basin, pouring basin or cup, flask, sprue, blind riser, core sand, cope, drag, mold cavity, runner, choke, gate, sand, parting line. So many components are there in this method. So in this method, we will have a sand casting. So this is the sand casting mold features. Next, they will have a sand casting method, mechanical drawing of the component. Cope, pattern plate, drag pattern plate, 4 boxes, 4 halls plastered together, cope ready for sand, and cope after ramming with the sand and removing the pattern, sprue and razor, drag ready for sand, drag after removing the pattern, drag with the core set in place. This is the setup of the entire setup of the casting. Casting mold is ready. Now you can able to pour the molten metal. After that, you can able to casting is removed from the mold and remove the unwanted portions like runner, razor, and other projections, flash, and all those things. Finally, you will get the product like this. This is the steps of sand casting process. So CO2 molding. CO2 molding is one of the most widely used molding process. So it is a kind of sand casting process. CO2 molding is a special molding process for making the molds and cores. The principle of this process is the chemical action between sodium silicate and carbon dioxide. Silica gel is formed when carbon dioxide reacts with sodium silicate. Hardening of the sand takes place, which gives molding strength to the mold because of the silica gel that has been formed. The bonding strength of the is sufficient to eliminate the drying or backing of the mold. So the chemical reaction between carbon dioxide and silicate is given by this formula. The sand used for the process must be dry or free of the clay. The amount of sodium silicate to be mixed with the sand must be around 3 to 5%. To enhance the collapsibility of the mold, coal powder, wood flour, and sea coal can be added as additives. In addition of iron oxide prevents hot deformation of pores and produces smooth interface between the mold and metal. In this process, carbon dioxide gas is passed through the mold for a predetermined length of time. The amount of carbon dioxide gas required can be calculated based upon the sodium silicate mixed with the sand. The flow rate of carbon dioxide depends on the depth of the penetration desired. Applications, parts of valves, pumps, compressors, machine tools, wheel castings, railway components, diesel engines, and gear castings. These are all the components we can able to make use of this carbon dioxide molding. We can able to prepare the end product like parts of valves, pumps, compressors, machine tools, wheel castings, railway components, diesel engines, and gear castings. Advantages: labor cost and floor space are saved by avoiding drying or backing of the mold. High accuracy and good surface finish of the casting are possible. Withdrawal of the pattern is facilitated since the molds may be hardened before extracting the pattern. Mold cracking and deformation are prevented. Process can be mechanized for mass production. Less skill is required compared to dry sand molding. Disadvantages: molds and cores are most expensive and they need convenient storing atmospheric conditions. Difficult to reclaim the sand. Life of the sand mixer is short. So next we will discuss about the shell molding process. Shell molding is nothing but small shells we can able to form with 9 mm thickness with help of a hot pattern and binders and some additives. And based on that shell, we can able to make a casting, that is the shell molding process. Shell molding is a casting process in which a mold is then shell, typically 9 mm, made up of sand held together by thermosetting resin binder. The surface of the shell mold cavity is smoother than the conventional green sand mold, and this smoothness permits easier flow of molten metal during the pouring and a better surface finish on the final casting. Surface finish of 2.5 micrometer can be obtained. Good dimensional accuracy is achieved with tolerances of plus or minus 0.25 mm possible on small to medium sized parts. The good finish and accuracy often precludes the need for further machining. Collapsibility of the mold generally sufficient to avoid tearing and cracking of the casting. Disadvantages of the shell molding includes a more expensive metal pattern than the corresponding pattern for green sand molding. Shell molding can be mechanized for mass production and is very economical for large quantities. Example of parts made using shell molding include gears, valve bodies, bushings, and camshafts, etc. Next is steps in shell molding. A match plate or cope and drag metal pattern is heated and placed over a box containing a sand mixed with thermosetting resin. Box is inverted so that sand and resin fall into the hard pattern, causing a layer of the mixer to partially cure on the surface to form a hard shell. Box is repositioned so that loose, uncured particles drop away, and shell is heated in oven over several minutes to complete curing. Shell mold is stripped from the pattern. Two halves of the shell molds are assembled, supported by sand and metal shot in a box and pouring to accomplished. The finished casting with the sprue removed. So this is the shell molding setup. Here they will have a heated pattern, will make in the top and then tilted the box, and it can able to react with the additives and other molding sand. They will have resins and other things. They can form a tilt the box, then they can form this type of thin shell. This thin shell will be ejected. After the ejection of thin shell, they will make some time for drying. After drying, they can kept like this in this flask. After that, they can able to pour the molten metal through this one. Then finally, they will get the product like this. Finished product will be obtained in this shell molding process. So investment casting. In investment casting, a part made up of wax is coated with refractory material to make the mold, after which the wax is melted away prior to the pouring of the molten metal. It is a precision casting process because it is capable of making castings of high accuracy and intricate detail. It is also known as lost wax process because the wax pattern is lost from the mold prior to casting. So, investment casting, since the wax pattern is melted off after the refractory mold is made, a separate pattern must be made for every casting. Why? Because the wax pattern is lost. Pattern production is usually accomplished by a molding operation, pouring or injecting the hot wax into a master die that has been designed with prior allowances for shrinkage of both wax and subsequent metal casting. In case where the part's geometry is complicated, several separate wax pieces must be joined to make the pattern. The high production operations, several patterns are attached to a sprue also made of wax to form a pattern tree. This is the geometry that will be cast out of metal. So, because many steps are involved in casting operation, it is a relatively expensive process. Investment castings are normally small in size, but parts with complex geometries can be cast. All types of metals, including steels, stainless steels, and other high temperature alloys, can be investment cast. Examples of parts include complex machinery parts, blades, and other components for turbine engines, jewelry, and dental fixtures. These are all the examples for investment casting. So, steps in investment casting. Wax patterns are produced. Several patterns are attached to sprue to form a pattern tree. The pattern tree is coated with a thin layer of refractory material. The full mold is formed by covering the coated tree with sufficient refractory material to make it rigid. The mold is held in an inverted position and heated to melt the wax and permit it to drip out of the cavity. The mold is preheated to a high temperature, which ensures that all contaminants are eliminated from the mold. It is also permits the liquid metal to flow more easily into the detailed cavity. The molten metal is poured, it solidifies, and the mold is broken away from the finished casting. Parts are separated from sprue. This is the investment casting process. This is a wax pattern. After the wax pattern, they will have a wax sprue. From this wax sprue, we can able to assemble number of wax patterns. Then they can able to make a refractory coating. After the refractory coating, it can be dried. After drying, invert this casting and heat is applied. So wax is entirely removed. After the wax removal, the empty spaces are provided. Mold cavity is there. With the help of this mold cavity, we can able to pour the molten metal. The molten metal will enter into the mold cavity and solidifies for some time. After the solidification, you remove the refractory and other coatings and other things. Finally, we will get the end product like this. This is the investment casting process. So, advancement in investment casting, parts of great complexity and intricacy can be cast. Close dimensional control, tolerances of plus or minus 0.075 mm are possible. Good surface finish is possible. The wax can usually be recovered for reuse, and additional machining is not normally required. This is a net shape process. Additional machining is not required in this process, though, so machining cost is saved. and permanent mold casting. Next one is a permanent mold casting process. The permanent mold casting uses a metal mold constructed of two sections that are designed for easy, precise openings and closing. These molds are commonly made up of steel or cast iron. The cavity with the gating system included is machined into the two halves to provide accurate dimensions and a good surface finish. Metals commonly cast in permanent molds include aluminum, magnesium, copper-based alloys, and cast iron, etc. So, however, the cast iron requires a high pouring temperature of 1250 degrees centigrade to 1500 degrees centigrade, which takes a heavy toll on mold life. The very high pouring temperatures of steel make permanent mold unsuitable for this metal unless the mold is made of refractory material. Pores can be used in permanent molds to form interior surfaces in the cast product. So the cores can be made up of metal, but either their shape must allow for removal from the casting or they must be mechanically collapsible to permit removal. If withdrawal of metal core would be difficult or impossible, sand cores can be used, in which case the casting process is often referred as to semi-permanent mold casting. The preparation of casting, the mold is first preheated and one or more coatings are sprayed on the cavity. Preheating facilities, metal flow through the gating system and into the cavity. The coatings aid heat dissipation and lubricate the mold surfaces for easier separation of the cast product. After pouring, as soon as the metal solidifies, the mold is opened and the casting is removed. Permanent molds do not collapse, so the mold must be opened before appreciable cooling contraction occurs in order to prevent cracks in the casting. So, steps of permanent mold casting process: mold is reheated and coated, cores if used. Sometimes core not used, or instead, and mold is closed, molten metal is poured into the mold and mold is opened, finished part we are obtained. So this is the steps in permanent mold casting process. Here they will have a movable section, the stationary mold section, spray nozzle. With the help of that one, we can able to clean the thing and you can arrange the force is applied and arrange the mold cavity. And after the mold cavity, you can pour the molten metal. This molten metal will enter into the mold cavity and it can able to solidify for some time. After the solidification, you should remove the movable mold section and finally we will get the product like this in this permanent mold casting process. So advantages and disadvantages of permanent mold casting processes. Advantages of permanent mold casting include good surface finish and close dimensional control. In addition, more rapid solidification caused by the metal mold results in a finer grain structure, so the stronger castings are produced. This process is generally limited to metals of lower melting points. Higher melting point metals we may not be able to do in this process. So other limitations include simple parts geometries compared to sand casting because of the need to open the mold and the expense of the mold. Because the mold cost is substantial, the process is best suited to high volume production and can be automated accordingly. The typical parts include automotive pistons, pumps, bodies, and certain castings for aircraft and missiles, etc. So die casting process. Die casting is a permanent mold casting process in which the molten metal is injected into the mold cavity under high pressure. The procedure produces a good surface finish and a good dimensional accuracy, and also it provides high volume output but with expensive tooling. Die casting highly susceptible for porosity based on how the molten metal is injected into the cavity. There are two main types of die casting machines: hot chamber die casting and cold chamber die casting. So this one is hot chamber die casting. This is hot chamber is inside the plunger. They will have a hot chamber is there. Here they can apply a molten metal plunger. With the help of plunger, you can apply a pressure and it can able to through this wire. It can able to reach it to the die and it can able to solidify for some time. Water jackets also provided. So then they can able to sometime it can solidify. After the solidification, the mobile die half is moved and eject the component. Finally, we will get the component like this. Eject the component and then ejector pins will be open and finally we will get this type of casting. This is the steps in hot chamber die casting. And next we will have a with a die closed and plunger withdrawn, the molten metal flows into the chamber. Plunger forces metal in chamber to flow into the die, maintaining pressure during cooling and solidification. And the plunger is withdrawn, die is opened, and the solidified parts is ejected. Finished part we are able to obtain. So like this. So this is the cold chamber die casting. Here also the same setup, and here only thing is with separate furnace we can able to make a molten metal through help of a ladle. We can able to pour the molten metal here. We can apply a ram pressure, and due to that pressure it can able to send to the dies place for the molten metal. It can able to solidify for some time. After the solidification, the movable die off is moved. And here they will have ejector pins are there. With the help of this ejector pins, we can able to remove the final component, and then we can able to make the required finishing operations and other thing. This is steps in cold chamber die casting. So with the die closed and ram withdrawn, molten metal is poured into the chamber. Ram forces metal to flow into die, maintaining pressure during cooling and solidification, and the ram is withdrawn, die is opened, and part is ejected. So low pressure die casting. The low pressure casting, the liquid metal is forced into the cavity under low pressure, approximately 0.1 megapascal from both beneath, so that the flow is upward. The advantages of this approach over traditional pouring is that clean molten metal from the center of the ladle is introduced into the mold, rather than the metal that heat has been exposed to air. Gas porosity and oxidation defects are thereby minimized. The mechanical properties are improved. This is a very important one. Mechanical properties, hardness, strength, ductility, and other properties, strength, and all those things we can able to improve. So low pressure casting, this is a low pressure casting. Here they can apply a chamber low pressure casting. With the help of that one, we can able to reach to the level of air pressure. Due to the air pressure, here the atmospheric pressure will act. Based on that pressure, here they will be able to make a fluid will enter molten metal. Molten metal will enter into the cavity, and the casting is solidified. After that, this can be removed, and then we can able to remove the final casted product. And a permanent mold made up of metal or ceramic is rotated at a high speed of 300. This is centrifugal casting. Next one is centrifugal casting. A permanent mold made up of metal or ceramic is rotated at a high speed of 300 to 3000 RPM The molten metal is then poured into the mold cavity due to centrifugal action. The molten metal conform to the cavity provided in the mold. Centrifugal casting, there are three types: true centrifugal casting, semi-centrifugal casting, and centrifuge casting. So this is the centrifugal casting setup. This will be rotated in high RPM up to 300 to 3000 RPM. Molten metal will pour here. So it can able to, due to centrifugal action, the edges of the walls, it can able to make a hollow pipes are formed. It can be high rotational rate. So, and dense cast we are able to obtain. This casting is usually a fine grained casting with a very fine grained outer diameter, which is resistant to atmospheric corrosion, a typical situation with pipes. Okay, inside the inside diameter has more impurities and inclusions which can be machined away. Only cylindrical shapes can be produced with this process. Typical materials that can be cast with this process are iron, steel, stainless steels, and alloys of aluminum, copper, and nickel. Typically, parts made by this process are pipes, boilers, pressure vessels, flywheels, cylinder liners, and other parts that are axisymmetric. Next, they will have a skews casting. It is also called extrusion casting, liquid pressing, pressure crystallization, and skews forming. Single step transformation of molten metal into dense and pore free components. It is a hybrid process which combines the advantages of permanent mold casting and die forging is a single operation. It uses a reusable die. So skews casting, the process parameters are metal or alloy to be cast, melt volume, die temperature, melt temperature, pressure, pressure duration, dead time, and lubricant or die coating. These are all the process parameters used in skews casting. Its advantages: near net shape process, porosity free, maximum yield, any alloy can be cast, better mechanical properties, good dimensional accuracy, economic process, potential for automation, isotropic properties. Its disadvantages: oxide inclusions, hot TS, over and under filling, and high tooling cost. These are all some of the disadvantages of skews casting. We will get the very dense cast we are able to obtain using this method. Applications: automotive skews cast components, missile nose cones, defense armors, fabrication of metal matrix composites, rail vehicle structural members, constructional support members. These are all the components with the help of skews casting. Frequently, we are able to manufacturing with the help of high density cast with defect-free casting. And they will have steps in skews casting, direct method, with metal movement, without metal movement, indirect, vertical clamping injection, horizontal clamping injection, horizontal die closing with vertical injection, vertical die closing with the horizontal injection. This is the block diagram, shows the skews casting classifications. Steps in skews casting: the metered quantity of metal, liquid metal, is poured into the preheated and well lubricated die cavity. The liquid metal is then pressurized using a suitable punch after a dwell time. Instead of punch, we can able to use hydraulic press also. The pressure is held on the metal until complete solidification take place. The punch is then withdrawn and the casting is ejected out. So this is the steps in skews casting. You can able to apply a pressure. Due to this pressure, it can able to direct method and indirect method. These are all some diagram for punch. Another schematic diagram shows two forms of direct skews casting process. and the steps in skew casting. The metered quantity of liquid metal is poured into a preheated and well lubricated die cavity. The liquid metal is then pressurized using a suitable punch. After a dwell time, the pressure is held on the metal until complete solidification takes place. Then the punch is then withdrawn and the casting is ejected out. This process based on principle of electro-slag welding, electro-slag casting. This process is based on the principle of electro-slag welding process. It depends completely with the raising and gating system and also with the need for separate melting unit, pouring, ladle, and transportation arrangements. This process consists of water-cooled iron or steel mold C, which itself acts as a melting unit, and the one or more consumable steel electrodes E to produce molten metal under a protective slag. Heat is produced by the passage of electric current between the electrodes and mold through the conductive slag D. The temperature rises above the melting point of the electrode. It melts and the tip and flows through the base slag into the molten metal pool B in the mold cavity. As the electrode gets consumed, it is continuously lowered at a controlled rate G. Solidification takes place without any contact with the atmosphere. So this is the electro-slag casting. This is an electrode. This electrode is heated. Die, they can able to deposit the layer by layer metal, and then after that they can able to get the electro-slag casting process. Besides refining action, the slag absorbs non-metallic impurities from the molten metal and protects it from atmospheric contaminations. The electrode maintains a continuous pool of metal on the top of the solidifying layer, and therefore feed metal is always available to guarantee of sound structure. Graphite and ceramic molds have also been used in the place of metallic ones. The transfer techniques has also been adopted, in which metal is melted under cover of protective slag in a separate chamber on the side of the mold. The molten metal flows continuously from the chamber into the mold cavity. This technique makes it possible to produce casting of complex shapes and composite forms. Typical items cast by this process are crankshaft, engine crankshaft, connecting rods, nozzles, valve bodies, high pressure vessels, etc. There is no limit to the size and weight of the casting that can be produced. The casting yield is almost 100%. However, the process is expensive owing to the high initial cost and high cost of electrodes, which have first to be formed in the suitable sizes and compositions. A water-cooled mold is used to make a long casting of constant cross-section. Liquid metal is poured into the mold against a starter block. As the metal solidifies, it is removed, exposing more liquid to the mold face. This is a continuous casting process. This continuous casting process, this is a molten metal, this is a cooled mold, and then they will have a cast ingots. These ingots will be, they can able to cooling is provided, and continuously it can able to get it, and they will have a whatever length you can able to obtain after the solidification. With the help of oxyacetylene flame, can cut the required size of the things. This is a continuous casting process. Here, ladle from the refineries. Here, this is a turn dish. With the help of this one, we can able to, this is controlled by sensors, and it can able to pour the molten metal in the continuous manner, and the inert gas, argon gas is passed, and water jackets are cooled, and the molten metal is poured, and these pinch rolls are withdrawn of the material, and required level of length is reached. After that, with the help of oxyacetylene flame, you can able to cut the material, or you can able to continuously, you can able to make the rollers with the help of that one. Straightening rollers, with the help of that one, you can able to straighten the length of the rod or bar or whatever it may be. So here they will have oxyacetylene torch. With the help of that one, record here a starting dummy is there. You can able to record the length of the object can be cut through this oxyacetylene flame and then stack into the rack. This is the one of the most important process in continuous casting process. Next, they will have a vacuum molding. Vacuum molding, also called as V processes. It is uses a sand mold held together by vacuum pressure rather than by a chemical binder. Accordingly, the term vacuum in this process refers to the making of the mold rather than the casting operation itself. Because no binders are used, the sand is readily recovered in vacuum molding. Also, the sand does not require extensive mechanical reconditioning normally done when binders are used in the molding sand. Since no water is mixed with the sand, moisture related defects are absent from the product. Disadvantages of V processes are that it is relatively slow and not readily adaptable to mechanization. So steps in vacuum molding: a thin sheet of preheated plastic is drawn over a match plate or a cope and a drag pattern by vacuum. The pattern has small vent holes to facilitate vacuum forming. A specially designed flask is placed over the pattern plate and filled with sand, and a sprue and a pouring cup are formed in the sand. Another thin plastic sheet is placed over the flask and a vacuum is drawn that causes the sand grains to be held together, forming a rigid mold. The vacuum on the mold pattern is released to permit the pattern to the stripped from the mold. This mold is assembled with its matching off to form a cope and drag, and with vacuum maintained on both halves, pouring is accomplished. The plastic sheet quickly burns away the contacting of the molten metal. After solidification, nearly all the sand can be recovered for reuse. So this is the steps in vacuum molding. Here they will have a vent holes for drop plastic. Here they will have a vacuum is there. You can able to air will be air with the help of pump. We can able to vacuum is generated. From this vacuum, we can able to pour the molten metal. So here they can able to make a forming, and after that you can able to make a assemble all the thing. Then you can able to pour the molten metal. Here vacuum is drawn, so it can able to get the good quality of the casting. So expanded polystyrene process. The expanded polystyrene process casting process uses a mold of sand packed around the polystyrene foam pattern that vaporizes when the molten metal is poured into the mold. This process and variations of it are known by other names including lost foam process. Why? Because foam is lost. Lost pattern process, pattern also lost. Evaporative foam process, foam is evaporated, and full mold process. These are all the other names for expanded polystyrene process. So the foam pattern included the sprue, races, and the gating system, and it may also contain an internal cores if needed, thus eliminating the need for a separate core in the mold. Also, since the foam pattern itself becomes the cavity of the mold, consideration of the draft and the parting lines can be ignored. The mold does not have to be opened into the cope and drag sections. Various methods for making this pattern can be used depending on the quantities of castings to be produced. For one of the kind of castings, the foams is manually cut from a large strips and assembled to form the pattern. The large production runs in automated molding operations can be set up to mold the patterns prior to the molding and molds for casting. The expanded polystyrene making process, the pattern is normally coated with refractory compound to provide a smoother surface on the pattern and to improve its high temperature resistance. Molding sands usually include bonding agents. However, dry sand is used in certain processes in this group, which aids recovery and reuse. The steps in expanded polystyrene process, pattern of polystyrene is coated with refractory compound, foam pattern is placed in the mold box, and sand is compacted around the pattern, and molten metal is poured into the portion of the pattern that forms the pouring cup and sprue. As the metal enters the mold, the polystyrene foam is vaporized aggregate of the advancing liquid, thus allowing the resulting mold cavity to be filled. So these are all the cup and sprue of the foam, and the foam pattern, and spraying refractory compound. Mold is placed here. Then they can able to pour the molten metal. Finally, we will get the tumble shape of the product. The advantages of expandable polystyrene process, the pattern need not be removed from the mold. This simplifies and expedites mold making. In a conventional green sand mold, 2 holes are required with the proper parting lines. Draft allowances must be provided in the mold design. Cores must be inserted, and the gating and riser system must be added. With the expanded polystyrene process, these steps are built into the pattern itself. So new pattern is needed for every casting. So the economics of the expandable polystyrene casting process depend largely on the cost of the producing the patterns. The process has been applied to mass produce castings for automobile engines. Automated production systems are installed to mold the polystyrene foam patterns for these applications. Fettling and finishing in context with the casting processes. Fettling means the removal of unwanted metal, example, flashings, razors, gates, sprues, runners, etc. After the casting has solidified and been removed from the mold, a number of additional steps are usually required. These operations include trimming, removing the core, surface cleaning, inspection, repair of required, and heat treatment. If they need for heat treatment, we can go for heat treatment of the casting final product also. Trimming is involved, removes sprues, runners, razor, parting line flash, fins, chaplets, and any other excessive metal from the cast part. In this case, brittle castings alloys, and when the cross section are relatively small, these appendages on the castings can be broken off. Band sawing, abrasive wheel cutting, or various torch cutting methods are used. In cores, fettling and finishing, in cores have been used to cast the part. They must be removed. The most cores are chemically bonded or oil bonded sand, and they often fall out of the casting as a binder deteriorates. In some cases, they are removed by shaking the casting either manually or mechanically. Larger castings, pneumatically or hydraulically also, we can able to shaking. In rare instances, cores are removed by chemically dissolving the bonding agent used in the sand core. Solid core must be hammered or pressed out. The cores have been used for cast the part. They must be removed. Most cores are chemically bonded or oil bonded sand, and they often fall out of the casting as the binder deteriorates. In some cases, they are removed by shaking casting either manually or mechanically or hydraulically, pneumatically. Rare instances, cores are removed by chemically dissolving bonding agents using in the sand core. Solid cores must be hammered or pressed out. The cores have been used in the cast part. They must be removed. Most cores are surface cleaning is most important in the case of sand casting. Many of the other casting methods, especially the permanent mold process, this step can be avoided. Surface cleaning involves removal of sand from the surface of the casting and otherwise enhancing the appearance of the surface. Methods used for clean and surface including tumbling, air blasting with coarse and grid or metal shot, wire brushing, and chemical pickling also. Defects are possible in this casting and inspection is needed to detect their presence, and other reference materials for different types of casting defects we will discuss in the later classes. These quality issues are considered in the following section. Casting are often heat treated to enhance their properties, either for subsequent processing, operation such as machining, or to bring out the desired properties for application of the part. Reading assignment for slag casting, plaster mold and ceramic mold casting, full mold casting process, pressure die casting, vacuum permanent mold casting, skews casting, and semi-solid metal casting. Enough for today's class. Thank you for your kind attention. So any queries, you can able to make a chat box. You can able to make a queries and we will discuss all those things. So today we are discuss about what are all the special casting techniques are there and their applications, limitations, advantages, and all those things. Thank you very much for your kind attention.